Oh, welcome back to another class in Unit 2 of Firing of Ceramics. In this unit, as you know, last time we did our first kill simulation, or maybe optimization, if you'd like to call it that. And today we're going to do our second one. The second one is going to be about calcining limestone, or calcium carbonate, calcite, as we call it. That's going to require an endothermic reaction when we calculate the heat required by the load in the kiln. So let's get started. As I told you last time, we were going to review the homework problem, the coils problem. And I hope you've had time to do this. I recommend that you do it on your own if you haven't, because in that situation, we get to work with the heat flow, E-solutions. Of course, what I meant to say is we're going to work these problems with E-solutions. And so let's take a look at some of the different things we can find with different lining configurations, with flues versus no flues in the furnace, and see ultimately where we can reduce the cost per pound of the heat treated steel. Now, I want to tell you that my father was an accountant, and that's why I'm not one. I'm an engineer. But I worked with accountants all my career, and I respect them. And someone has to look at the numbers, crunch the numbers, and accountants are always going to be looking at cost per unit weight or volume of a product. And so that's what we're going to take a look at today. And here's the result of the different problems where I gave you a case one. And then I went about the business of adding a flue. Okay, then I went about adding the business of using insulating fire brick in the walls, changing the lining configuration. Had a very traditional lining configuration in case number one, but I went to case number two, old-fashioned products in case number two. In case number four, I did case number one, but I added a coil. So I went from 2 coils of steel to 3. I'm increasing the load in the furnace. Many of you can quickly predict what's going to happen. In case number 5, I took case number 4, but now I use ceramic fiber, CF, ceramic fiber in the sidewalls. Okay, so we know that's going to mean less heat storage and less heat conduction through the walls. Case number 6, I doubled the heating schedule and still had the 3 coils. And case number 7, I'm going to do 2 things, is I'm going to add a coil. So now I have 4 in the furnace, because there's plenty of freeboard in the furnace, plenty of height in the furnace chamber to allow me to do that. And I've also reduced the thickness of the ceramic fiber. So you can pause this presentation and print my answers. I won't say I've done the best job I can of doing good arithmetic calculations. You might catch an error from here to there. I understand that. So I hope I did them right. So if you pause and print, then you can resume when we take a couple of observations at what we have seen here. The first observation had to do with the effect of the flue, because for convenience, we'd been designing furnaces without a flue, without a smokestack or chimney. But in the real world, of course, we can't do that. With gas-fired furnaces, we've got to have a flue. And so I just wanted to see how that affected things. And so you can see here at the wall losses, when I added a flue, the wall losses went up. Well, what the program is doing is accounting for higher velocity in the furnace against the walls, because we have a movement of combustion gases through the furnace and the pressure is being relieved. So maybe it makes sense that the wall losses would go up. Interestingly enough, the heat storage went down a little bit. Okay, well, some of the heat's being conveyed by stack losses through the stack. And so I suppose that is the reason why that happened. So in case one compared to case number two, I actually had a little energy cost decrease per pound. Okay, and that's only because I'm using the energy more efficiently with the flue. I wanted to show you this just to show you that the numbers change a little bit when we do a model without a flue. But for convenience, I've tried to make these problems as simple as possible and not include a flue. Okay, so here we compared a couple of different insulations in case 2 and 3. Case 2 was a flue, and in that particular situation, a castable backup insulation on the walls. Remember, the walls had hard brick or super duty brick or high heat duty fire brick, whatever you want to call it. On the inner lining, that's the refractory exposed to the high heat inside the furnace, and castable on the outside of the lining adjacent to the shell. Well, in this case, I just put insulating fire brick adjacent to the shell. And you can look at these total heat requirements here. And with the castable, the total heat requirement is predicted as a little bit less. And that's probably because the apparent porosity of the castable is a little bit higher than it is in the insulating fire brick. So nevertheless, that was the result. It saved in cost per pound about 1%. And of course, saving 1% is probably not going to be terribly interesting for you if you already have a furnace lined in one particular configuration. More interesting one is over here. And these are a lot of different numbers right here, but particularly when you go across here, we're going from 2 coils. We're going to add another coil. And if you go down here to total BTUs per pound of steel, I abbreviated steel, STL period, then adding another coil, increasing the furnace load, really reduced the cost per pound of finished product. Nevertheless, if we skip over to the last one, I added another coil. So now I have 4 coils in the furnace. And you'll note that I also made a change in the insulation and the sidewalls. I just had a very relatively thin 5-inch ceramic fiber sidewall in the furnace. And I really reduced the cost per pound by as much as 53%. And some of these others, I played some games with the refractory insulation, and this is basically asking what if I change the refractory insulation in an existing furnace to optimize the fuel utilization, optimize the cost per pound of finished product. And that's really the main advantage of these simulation programs, is you can quickly and easily take a look at questions like this. Well, let's get about doing our second simulation. We're going to calcine limestone. We're going to find the energy required when creating lime, that's decomposing calcium carbonate, creating calcium oxide by heating or calcining 8,000 pounds of limestone, either using a periodic kill, a batch kill, an intermittent kill. You put the product in this case in the saggers, you're going to put it on the kill car deck. We're going to roll it into with the shuttle kiln. We're going to heat up the kiln. We're going to kill off the kiln and get the product out. That's the intermittent kiln. Or we're going to put it in a continuous kiln, this time a rotary kiln. Well, I think this is a pretty interesting problem. Before I get started, I'm going to confess to you a mistake I made when I was a second-year student in ceramic engineering. So the old department head came out to me and said, Brosnan, go out there and calcine 100 pounds of limestone. I need some lime. So I was supposed to do this in a gas-fired kiln, laboratory kiln. So I went and took a refractory sagger, like these that are stacked up right here, used in ceramics. And I filled it up with limestone. And I heated up the kiln. Now, in my defense, I had not taken phase equilibrium diagrams yet. And so I didn't know what happened in the lime and alumina and silica phase diagram. So if the sagger's over here, an aluminosilicate ceramic sagger, and I'm putting lime in it, guess what's going to happen? The lowest melting eutectic is going to happen over here at about 1170 degrees Celsius. It doesn't matter what the refractory composition was. It was probably around here somewhere. But remember, the first liquid that forms is going to be at the lowest melting eutectic in the system, even though that might be off the overall composition of the refractory and the direction of lime to the refractory. You're going to get that one right there. And guess what? If you have some alkali present, you're going to reduce that temperature to about 1070 degrees Celsius. So you can guess what happened. I had to sit there with the kiln because we didn't have any safety controls on it in those years. It was a laboratory batch kiln. And so we said we were babysitting the kiln at that time. We might have had some beverages of our favorite choice with us, but nevertheless, when the kiln got up to red heat and held there for a period of time, I thought the job was done. I turned it off and took my beverage cans with me and went back to the college dormitory. The next day, the department head was mad as a wet cat, a wet hen. He was so mad at me, he was yelling at me. He said, come look and see what you did. Well, of course, what happened was the lime reacted with the sagger, melted through the sagger and messed up the hearth of the kiln. I was responsible, but I didn't know anything about the reaction between lime and clay refractory. And so I thought I was innocent. It took me quite a while to live that mistake down. And when I took phase equilibrium diagrams, I began to understand my mistake of the past. It turns out that in my career, I've used this calcium oxide or lime aluminum silica phase diagram many, many times. And so I understand it very, very well. But nevertheless, I wanted to admit that about my lime calcination experience. So also it's useful to say that in North America, and using American English, which many of you might think of as not proper English whatsoever, that's your business, but nevertheless, we use the word lime in a generic sense. We can refer to lime as limestone, which is calcium carbonate, usually in the form of calcite, the crystalline form, except for seashells. There's another form called aragonite, which are less soluble in seawater. The mollusk of the world, the shelled animals of the world like that. They'd rather have aragonite than calcite, but we're going to calcine calcite because that's the form much of the limestone rock is present in our world. We also use the term lime to talk about ag lime, agricultural lime, or hydrated lime, calcium hydroxide. We also use the word lime to talk about calcium oxide when it's lightly calcined and very reactive, meaning it's been calcined to the decomposition temperature. And we also used that term to talk about something called dead burn lime, which is heated to much higher temperatures to form larger crystals and to redistribute the impurities of the limestone so that the impurities inhibit the hydration in the atmosphere with moisture in the atmosphere. So that kind of material is sold in bulk and used in a lot of industries, for example, the steel industry. So right now, what we're really talking about is taking limestone and making caustic lime, just decomposing the limestone. And the chemical reaction is pretty easy. Calcium carbonate as a solid goes to calcium oxide as a solid and liberates carbon dioxide. Now, of course, carbon dioxide we know is a global warming gas, and many people are sensitive to that. Of course, many times the lime that's created will recarbonate in things like masonry mortars and concretes and things of this nature. So it captures the CO2 back, at least in part. Now the gram molecular weights of calcium oxide is 56 grams per mole. The gram molecular weight of calcium carbonate is 100 grams per mole. So basically 100 parts by weight creates 56 parts by weight of the caustic lime, the calcium oxide, in this reaction. Now further, we're going to assume this reaction takes place at 1800 degrees Fahrenheit. That's just for convenience and calculation in the problem. It actually takes place a little lower than 980 degrees C, somewhere in the realm of 600 to 800 degrees C. But I'm pretending, just for the purpose of this problem, it takes place at 980 degrees C, or about 1800 degrees Fahrenheit. So I only have to do one specific heat calculation. And I'm also saying that that's an endothermic reaction. To decompose the compound calcium carbonate, it requires heat to form calcium oxide, and it requires 725 BTUs per pound of limestone. Now, we've got to be very careful during working this problem that we're working on a basis of pounds of the feedstock or pounds of the product. Most of the accountants of the world, of course, don't want to work in terms of pounds of product because that's what you sell. Okay, we call this calcination. So I borrowed this definition from the internet. It's the process of heating a substance to a high temperature, but below the melting point, fusion point, causing loss of moisture, chemical reduction, or oxidation, or dissociation into simpler substances. So that's exactly what we've got right here. This definition says the term calcination was originally applied to the method of driving off carbon dioxide from limestone to obtain lime. Now, societies have been doing this for I don't know how many thousand years in making masonry mortars. I think it goes certainly back to the Greek Empire, Roman Empire, then the Greek Empire, into the Middle East, when people learned that they could burn or calcine calcium carbonate to make a masonry mortar. So here's our problem. Now, if you're going to work along with me, you might want to pause this presentation from time to time and print out the problem just to make it easy for you to follow along, so you can pause anytime. So the furnace is going to be heated from room temperature, ambient temperature of 70 degrees Fahrenheit up to 1800 degrees Fahrenheit. That's the decomposition temperature. And we're going to heat at 150 degrees Fahrenheit an hour. That's on the high side of heating most refractory linings. Certainly acceptable by many industrial recommendations. 150 degrees an hour, and then hold the furnace for 5 hours at 1800 degrees Fahrenheit. After the 5 hours, we shut it off and let it cool to room temperature. We're going to say this furnace has no flue, just to make the problem a little bit easier for you. So we're heating it up from 70 to 1800. That's a span of 1730 degrees Fahrenheit. And heating it 150 degrees Fahrenheit an hour, that takes 11.53 hours to heat it up. Once we get to that temperature, as we said, we're going to hold for 5 hours. As far as dimensions, this furnace is 6 feet wide. The kiln car or hearth is 8 feet long, and the height of the kiln is 6 foot. So it's a fairly small lab or pilot plant kiln. The crown has ceramic fiber, 12 inches. Usually put a little bit more of that in the crown since heat rises. The sidewalls, 6 inches of ceramic fiber or rigid CF, of course. And the hearth is 6 inches of castable insulation over 3 inches of insulated firebrick. So usually we're going to put a dense material on the hearth to be a load-bearing material that's going to take mechanical damage from the loads put on it. So we're going to put a strong material there, and I put it over 3 inches of insulating firebrick. Remember, 9 by 4.5 by 3 is one of the dimensions of the standard brick in the United States. So we're using the large flatwise surface laid flat on the car deck and casting castable on top of that, drying it out and then using it. The load is 8,000 pounds of limestone put in 80 ceramic saggers. So each one is going to weigh 100 pounds. Specific heat, here's limestone and the saggers. So that's going to allow us to do the calculation. Now, as we did last week, of course, when we do these calculations, we're looking for the total heat required. We're going to look at that required per hour and required per unit weight of product. But the total heat required is always the heat required by the load. That's what's in the furnace. Sometimes people call that the process burden. You can use whatever words you want, but I usually call it the load. The heat required by the load plus the furnace heat storage plus the furnace heat loss. That's our definition that started out a long time ago with the law of conservation of energy. So here are the questions, and I just did them 1, 2, 3, 4 for you to make it easy in your calculation. So we start out trying to get the total heat requirement by the load. You're going to find out we're going to be working with millions of BTUs. So my symbol for million BTUs is MMBTU. Then we're going to get the heat required by the furnace, add it up, total the heat requirement by the load and the furnace, and we're going to take that total amount of heat and divide it by the finished product weight to get the BTUs per, in this case, pound of finished product. So here we go. Heat of the limestone, 8,000 pounds times its specific heat times a span of 730 degrees Fahrenheit gives us a total of 3.31 million BTUs to heat the limestone up to the temperature where it's going to decompose from room temperature. We had this theoretical decomposition temperature of 1800 just to make the problem easier. We're going to have to heat the saggers. That's what's holding the limestone. So we've got 8,000 pounds of them, 100 pounds of sagger. Probably chose that to make the calculation pretty easy. Specific heat of 0.19 times 1730 degrees Fahrenheit. That turns out to be 2.63 million BTUs to heat the saggers. And of course, we've got the enthalpy of reaction or decomposition of the limestone. So 8,000 pounds of that times 725 BTUs per pound at 1800 degrees Fahrenheit gives us 5.8 million BTUs, and we add this all up. And if my arithmetic is correct, we've got 11.74 million BTUs in order to change the limestone from calcium carbonate to lime when it's held within refractory saggers in a furnace. Heat required by the load plus the heat storage and the heat loss in the furnace. So here we go, setting up e-solutions in a rectangular furnace according to the refractory lining that I've given. That's hard for me to read, and you might be using a small screen to look at this. So I've just cut and paste some of the parts of this out. And so you can see our furnace lining here and the two component hard castable over insulating fire brick hearth in the furnace. So you're going to see the dimensions here. 12 inches of ceramic fiber, 6 inches of ceramic fiber in the sidewall. There's the 6 inches, 6 inches of castable here, 3 inches of insulating fire brick. According to the model, we'd have a surface temperature of 121 degrees Fahrenheit on the crown, the shell temperature, 162 degrees Fahrenheit on the sidewalls. Well, this is not as thick on the sidewalls. And we get 250 degrees Fahrenheit surface temperature on the outside. This also gives us the interface temperature. And we've learned to make sure that interface temperature is not above the refractoriness of the lesser refractory component. And of course, it's certainly not in this particular model. So from this, you can read the total furnace heat loss, 64,325 BTUs per hour. So 64,325 BTUs per hour times 11 hours of heating up is going to be 0.742 million BTUs. We're going to have a heat storage of 640,000 BTUs in the storage. Now we're going to add all these up. The heat loss by the furnace. Okay, we just calculated that. The heat storage by the furnace and heating up to 1800 Fahrenheit. But now we've got to deal with the dwell time. 5 hours times the furnace heat losses. Let's go back. Furnace heat losses, I went back too far, pardon me. Furnace heat losses, 64,325. So once you reach the soak temperature, the highest temperature, we're going to keep losing 64,325 BTUs per hour times 5 hours. That whole is going to cost us 0.32 million BTUs. So we add all that up, and the total heat required by the furnace is 1.7 million. Well, if we add the 1.7 million to the 11.74 that we already determined by the prior calculation, we come up with a need of 13.44 million BTUs to conduct the process in the furnace, given the refractory lining and the saggers that we used. Now, we got to express that on a finished product weight basis. So we started with 8,000 pounds of limestone, but we only get 56 pounds of lime per 100 pounds of limestone, or 0.56. We actually made 4,480 pounds, 4,480 pounds of lime, caustic lime. So over here, if we take the 13.44 million BTUs and divide it by the 4,480 pounds of caustic lime we made, then we will have expended 3,000 BTUs per pound in making that product. So this number 10 is the BTUs per pound of finished product. Okay, I showed you my calculation and got 3,000 BTUs per pound. The way we've done all the problems. The heat requirement is the heat required by the load plus the heat loss plus the heat storage. That's what we got, 3,000 BTUs per pound. Now the accountants may be breathing down your neck and may saying, we got to figure out a way to reduce that. That's a little too much energy, too much cost. And so problem B in this little simulation is a horizontal rotary kill. Now, eSolutions will do a vertical kill, and it will do a horizontal cylindrical kill. We're going to use a horizontal rotary kill. They're used quite a lot for calcination in the industrial world. So the limestone is fed to an elevated end of the kiln, which is turning. The turning kiln causes the limestone to rotate. That's helping the heat transfer in the process, and it tumbles its way down the shell, the kiln shell, which is refractory lined, toward the exit end and falls out into a cooling grate. Typically in rotary kilns, a burner is fired in the lower end, so the limestone is moving down the kiln counter current to the direction of the heat, moving up the kiln as the kiln is slightly elevated. Now, I just don't know if everyone has seen rotary kilns before, but here's the diagram of one I found on the internet. So here's the feed into the rotary kiln, and the kiln is turning and tumbling the product as it rotates round and round. You can see the burner on the exit end of the kiln. Here's where the material falls out of the kiln into a cooler. So the lime, in our case, is heating up as it's tumbling around and eventually being calcined. Okay. So given that, the kiln is driven, in this case, with a chain drive. Most of the larger rotary kilns have a sprocket out here with a drive gear down at this position. Of course, the supports are called trunnions, and they're just rollers that roll on a tire going around the kiln to cause the rotation. So it's a real problem that we're doing, even though the size of our rotary kiln is pretty darn small. 6 foot diameter by 20 foot long. You know, I know companies that have these things as laboratory kilns. Okay, that size. So that's not very big at all. We're going to feed 2,000 pounds an hour. We're going to model this for an hour. We're going to assume no openings in our model. And, well, we're going to ignore the heat storage. This is a refractory lined vessel. The steel shell itself is usually pretty thick to resist deformation and turning. Nevertheless, we're going to ignore that because we're going to say that the energy storage over much larger quantities of product than we're looking at would cause that storage to be a very low number. So we're going to be interested in the energy loss. The furnace insulation in our case is 12 inches of fire clay brick, lining the cylinder, internal diameter of the rotary kiln for heat protection, thermal protection of the steel shell. We're going to work this problem on the basis of 1 hour of production. Another reminder that 2,000 pounds of limestone becomes 1,128 pounds of lime when we calcine it. Now, there are a lot of issues that we're ignoring, like dust being lost through the draft, going up to maybe some dust collection device. We're just going to assume 100% of the product falls into the cooler. So I thought I'd say to you, why are we using hard fabric in this rotary kiln? Well, the reason is that limestone is very abrasive. Okay, we're banging rocks around inside this kiln as it turns, and they're falling down and striking refractories. So hard refractories typically have a lot of abrasion resistance. Now, having said that, refractory suppliers are going to say, well, we make abrasion resistant castables that can be used. Okay, I understand that, but I was just trying to make this problem simple. And you get into higher temperature kilns, then those operating at 1800 degrees Fahrenheit, you're going to use more heat resistant refractories in the lining. Certainly that's true of Portland cement kilns that use zones of firing, but the highest temperature zone typically is a magnesium aluminate or spinel refractory in today's world, mainly to resist the abrasion in the kiln. Of course, Portland cement kilns use internal elements called chains in the kiln, banging around with the Portland cement meal or mix that's coming into the kiln to try to improve heat transfer. So hard linings are necessary in these types of kilns, and of course, they have to resist stresses caused in rotation with the shell deformation and things of this nature. Well, here's the product statement. So you might again want to pause and print this for your use if you do a screen capture, but like everything else, we're going to look at the heat requirement from the process burden or the load. We're going to do that on a product weight basis. We're going to use e-solutions to get the heat loss in this product. We're going to get the total BTUs required on a product weight basis. And then we're going to compare it, what we got with a rotary kiln to what we got with a batch kiln, intermittent kiln. So this is pretty easy for us to do. The load requirements simply are what we had before, except we don't have any saggers this time. Okay, so this is the result we got before for heating the limestone. And it looks like I used 8,000 pounds instead of 2,000 pounds in an hour. So you might want to think about that and adjust that a little bit. I used 8,000 pounds here for decomposition. So my number is going to be high at 9.11 million BTUs. Well, at any rate, when I took my number of 9.11 million BTUs and converted it into product weight, I came up with 2,033 BTUs per pound. Okay. Well, I guess using 8,000 pounds here and 8,000 pounds didn't hurt me because I'm only looking at the product weight. So it doesn't matter that I made a mistake on the weights here. Okay, so now we, of course, set up e-solutions, but here we set it up for a cylindrical shaped furnace. And I came down here and clicked horizontal. So I've got the dimensions of the kiln shell right here, furnace temperature 1800, ambient temperature 70. I picked US units or inch pound units for our comparison here. Okay, so you're going to have the insulation set up. One thing that e-solutions does is it shows you the sidewall in the vertical part of the picture. Okay, so that's the fire clay refractory, and it's showing you an end to the kiln on a feed end, one of the ends, and an end to the kiln on the other end, a burning hood end. So nevertheless, it's a little different orientation. I like it better if it were inverted 90 degrees, but that's what it's going to show you. And so then we can look at the solution. This time I've tried to label this just to make sure the ends are clear and the cylindrical wall, the cylinder wall, or the rotary kiln wall is shown in the vertical here. And like I did before, because that might be hard for you to see, I've cut and paste, particularly so you could view this on a smaller screen device. And you can see that in this particular instance, we're going to show a pretty high temperature on the rotary kill shell. Now, people that operate rotary kills are very concerned about keeping these temperatures below points at which the kill shell can deform, because that can cause an outage in the kill. You're going to have to go in and stop the process and replace the section of kill if it gets a deformation or wrinkle in it. So this is very important for us, and of course most rotary kill operations are going to have some kind of sensoring device monitoring that that doesn't allow you to exceed that temperature. Bricks fall out of rotary kill linings from time to time, and people put high pressure air onto the kill shell, air horns as they're called, to try to cool the shell to keep in operation as long as they can. The engineering of a brick lining for a kill is very important, with keys and arches or wedges to make it the most stable lining. Okay, so the ends, the firing hood, if that's on this end, is $395 on the outside. The feed end is $395. The interior is $1,800. Okay, so we've shown everything in this orientation that eSolution gives us. Now the heat loss is 527,594 BTUs per hour. Okay, we've got some heat storage, 19 million BTUs, but just for example, while that's a big number, most rotary kill operations are set up to run 50 weeks a year with a 2-week outage, maintenance outage over the end of year holidays. So given that, if you operated 50 weeks a year, making the amount of limestone that we're making, spreading out that heat storage over that large amount of product would be a small amount, and perhaps even the accountants might let you get away with that. Heat losses, however, at 0.53 million BTUs per hour are something that we have to factor in. So it looks like that my slide for, there we go, found it. My slide for the result was missing, and so sometimes we'll hit the wrong PowerPoint button and delete a slide. So I just backed up, and there it is. So the heat required for the material, BTUs per pound, even though I used 8,000 pounds in the model and didn't need to, I should have used 2,000. Per pound, it's going to work out 2,032 BTUs, the heat required of the load per pound. Now the heat loss in the product we just read on eSolutions, 0.53 million BTUs per hour. So if we produce 2,000, if we are using 2,000 pounds of feedstock per hour, converting into 1,120 pounds of product, if we divide that out, we'll come up with 474 BTUs per pound of product. This is in BTUs per hour, but it's equivalent to 474 BTUs per pound. You'll see that 474 down here again when we add everything up. So the total required for the rotary kill process has to be the requirement of the load, 2,033. There's the 2,033 plus the requirement in the heat loss, 474. That adds up to 2,507 BTUs per pound. Okay, well, interestingly enough, that's certainly a number that people that track cost can use, but for fun of it, let's compare this energy savings when using a batch process. It took us 3,000 BTUs per pound in a batch kiln and 2507 in a continuous kiln. So if we look at the reduction in energy by the little formula here, it turns out to be about 16.5%. Now that's enough to make any accountant happy. And so therefore, we've compared two different processes making the same product. What we didn't do was play around with the types of products used in the process. We certainly could do that. In the intermittent kill, batch kill is a little more difficult situation. Not terribly difficult because this is not a very high temperature kill, but no, nevertheless, those are the results we got. So I think it's a pretty neat comparison. So we started out by asking the what if question with process burden and different types of insulation. We're using e-solutions here. We, using our little what if simulation, predicted an energy reduction of as much as 53% if we maximize the load in the kiln and play some games with the refractory lining configuration. Now I got to say that when I was a student, maybe you get tired of me saying this, but we had to do all this by manual calculation, and that homework that you did, looking at several different cases, would have been hours upon hours upon hours of manual calculations. And you were able to do this in probably an hour or less. So that's one of the advantages of the simulation software. Well, now we looked at a calcination process that included an endothermic reaction. Most ceramics are going to have some sort of endotherm, particularly clay ceramics, because we have to supply heat for dehydroxylation of the clay. So that was something new in calculating the total heat requirement. And then we compared a rotary kiln process to a batch kiln process and looked at the energy consumption. The way to produce energy is to go to a continuous process, and that's the best and actually the most obvious way, since the rotary kilns have been around for a long, long time. So you could say, well, we found out what we intuitively knew was going to happen, but it's nice to see the numbers. And one of the things about e-solutions is it provides us with at least realistic numbers to consider. So I hope you've liked that particular part of this simulation. Next class, we're going to look at another batch kiln. This is the big kiln in my laboratory at the university. We're going to run it in a simulation and figure out how much energy is required. And then we're going to do a test firing and read the gas meter before and after the test and see how accurate it was. So that should be interesting to you. We were in essence testing the model. So there's no homework for this time. Next time we're going to do the third and final kiln simulation. And then there'll be one class after that talking about firing defects and some environmental emissions, things like that, and kind of a summary. So 2 more classes after this, the last simulation next time. I wish you well.